Before continuing, let me remind you of two steps that we have already climbed. First, in the previous series, the principle of responding to damage to conductors and connections was noted. The short wording reads: shutdown in case of breakage, deterioration of conductivity and arc is provided if balance of the differential sensor currents is achieved only if there is no damage to the connection circuit. Second, the basic element for creating an automatic controller is presented. It is a differential dipole that is assembled when two poles of a standard differential current device are directly connected in series to each other. I emphasize that the direct connection is important. Sequential switching on of poles through the load is performed everywhere. This is the usual scheme. In a differential dipole, we carry the load beyond the two poles, so we get a new original design from the standard device. Naturally, we only use devices that do not depend on the power supply voltage. Correctly, they are functionally independent of the mains voltage. It remains to add a resistor, and the differential dipole will protect individual conductors from damage, and its efficiency in sensitivity and in trip time is an order of magnitude higher than that of known arc fault detection devices, AFDDs. Moreover, the device works equally in the zero and phase conductor, reacts to the first violation of conductivity or interruption without a lone arc, without multiple sparking. The beneficial properties of this simple solution we shall now try to apply for the protection of single-phase and multi-phase systems. For this purpose, we combine several differential dipoles with a common differential sensor, for example, a transformer. It turns out that in such a combination, the dipoles do not interfere with each other in any way. Moreover, they perfectly coexist with separate poles. A variety of options is not limited. You can divide an even number of poles into dipoles, or you can divide a part among an odd number. They will work together and will not upset the balance of the differential sensor as long as the system remains closed and there are no damages to the connections. Let's see how this is implemented and check the example of a serial 4-pole residual current operated circuit breaker. On the stand, two poles form a dipole. Power is supplied from above to the second and fourth poles via an autotransformer. The value of the rated residual operating current is 100 milliamps. The load is attached by means of plugs and sockets. They are also connected from below to the second and fourth poles via a loop and automatic circuit breakers. For the organization of control, the free terminals of the dipoles are connected to the terminals of the same name of the extreme outlet through auxiliary resistors. Thus, the loop is covered by auxiliary conductors along its entire length. In the first experiment, we simulate the breakage of conductors. We turn on the device under load. By using an automatic circuit breaker, we interrupt the zero working conductor. The device is activated immediately. Complete power shutoff is provided. Repeat the experiment. Now we break the phase conductor. It also provides the full protection from breakage. Next, we check the performance at low voltage. We obtain that for a load of 800 watts, the sensitivity to breakage is maintained at a voltage of 90 volts. For a 40-watt load, the minimum voltage was 115 volts. The following experiment simulates a connection failure due to the sliding contact of the conductors. The slide itself will be obtained using electrodes, one of which will be stationary and the second one to be part of the pendulum. For comparison, let's add an AFDD arc fault detection device. The voltage relay is used here only for monitoring power indicators. Immediately after switching on the load, our device worked and the AFDD didn't notice anything. The sliding contact produces an arc, but the lamp current was less than 0.2 amperes, when a minimum of 2.5 amperes is required to rock the device according to state standard 62606. We have already discussed this. Use the probe. There is a disconnection from it, so the device is working, but it is useless. The device doesn't feel an obvious damage to the power line. And our circuit breaker is perfect, and it worked as it should, and the test button works. Always with you. You will not lose. Let's go further. Increase the current and enter the operating range of the AFDD. Let's make sure that the data obtained is reliable at current of up to 6 amperes. We will also check at the upper limit of the permissible current of conventional outlets. Everything repeats. The AFDD does not work. Our device provides an instant response. Here it is appropriate to open a slide from another of our films and see what problem we have solved. Let me remind you that the problem with the AFDDs according to state standard 62606 was that they could not turn off the power at the initial stage of the accident. They hit the tail, so to speak, when the shutdown became useless. In comparison with the arc generator with carbon electrodes, we actually see single sparks and sticking of the electrodes on copper and aluminum. To detect such damages, the sensitivity of differential current devices is just required. They are at our connection structure, can timely prevent the dangerous development of events, as there is a control of the first single sparking. The next experiment will repeat the simulation of the situation with an increase in the transient resistance. Put a powerful 2.5 ohm resistor in the gap of the phase conductor. The tester shows the voltage on the load. In other words, it takes into account the drop on the resistor. We change the load stepwise. We see that at a current of 2.4 amps, the voltage has dropped by 10 volts and the protection is not yet triggered. Shutdown is performed at a current of about 6 amperes, just at the time when losses on the resistor could lead to heat and fire. We prevented this, and the AFDD is inactive. Another useful property is found in a link with a voltage relay. Let's see, when the voltage increases, an interruption occurs at the set limit. The differential current device is triggered simultaneously because it has registered a line break. The same thing happens when the voltage is lowered. Since the voltage relay is located after the differential current device, automatic reactivation is excluded. If you remember, we used to achieve this effect differently by swapping the relay inputs and outputs. If desired, automatic reactivation can be maintained. For this, the relay must be located before the differential current device. Let's finish the experiments with the demonstration of compatibility with sensors. Here, the outlets have thermostats nearby that work at a temperature of 60 degrees, heated with a hair dryer. In general, all the options for connecting fire and emergency automations are saved. We talked about full compatibility in many films, but we can only add that there are many suitable detectors, pressure sensors, humidity sensors, leak sensors, and thermostats. Moreover, they are placed in engines, instrument housings, and even in the smallest adapters. A dozen different schemes of connection of sensors can be found in the description of the patent. The link is in the explanation to the film. Let's summarize with the table of functions, which shows a significant addition to the protection capabilities. In fact, it is proved that with a dipole connection, one standard device replaces an entire control cabinet. overlaps the characteristics of known AFDDs and can protect individual conductors as well as single-phase and multi-phase networks. Well, smart bird, did you listen? Finish. I hope you understand the task, wise-sided magpie. Fly, tell everyone.